Uniform random numbers are real numbers that are distributed in an unpredictable manner, but evenly in a specific range. They're very simple to generate. For this reason, they're basic building blocks that we will use to generate random numbers with more complex distributions. For uniform random numbers, the value of the PDF is the following. The PDF is equal to 1 if u is in the interval 0, 1 and 0 otherwise. The CDF at u will be equal to 0 if u is smaller than 0, u if u is between 0 and 1 if u is larger than 1. So that would be this dependence. The inverse of the CDF, evaluated at the probability level p, is equal to u. P is a probability level, therefore it is between 0 and 1, and u will be in the support of the distribution, so also between 0 and 1. To generate a random number from a uniform 0, 1 distribution, we will use the function rand. This is a demo to illustrate the use of the built-in function rand. To generate a sample from a uniform 0, 1 distribution, we just type rand and intro, and we get a value sampled from the uniform 0, 1 distribution. We can generate a new sample, independent of the previous one, by typing rand and intro again. We get a different value. To generate a matrix with m rows and n columns of uniform 0, 1 samples, we just use this command, rand, parentheses, m, n, close parentheses. M and n have been previously initialized. Here is the matrix of 3 rows and 5 columns of pseudo-random numbers from the uniform 0, 1 distribution. We can get reproducible results in different numbers of ways. To get reproducible results, we store in S0 the state of the pseudo-random number generator. We now generate a couple of samples and we get these values. To generate the same sequence, we set the state of the random number generator again to S0. We sample again and we obtain the same result. Let's generate a sample of uniform 0, 1 random numbers and analyze its properties. These are samples from a uniform 0, 1 distribution. The bars in light blue are counting the number of samples that fall in a particular region within the 0, 1 interval. For instance, this first vertical bar is counting how many samples fall between 0 and 0.2. This second bar is counting how many samples fall between 0.2 and 0.4, and so on until 1. Once we have generated all the values in the sample, the bars form what is known as the histogram of the sample. If we follow the profile of the histogram, we see that it traces the PDF. However, the height of the bars is not exactly equal to 1, as what the PDF would predict. There are differences. This is related to the fact that our sample is finite. This type of error, for instance here, here, and here, is referred to as a fluctuation error. The size of the fluctuation becomes smaller as the sample grows. In particular, they decrease as the square root of the size of the sample.